Good afternoon, January 12, 2015. This is MATB110, Sections 1, Calculus 1. Today is the first class in the second week of the semester. So let's get started. Well, good afternoon. Sometimes we need to do it again. So welcome back to this class, the second week of the semester, Calculus 1. So if you have been attending to the photo environment as advised, you will discover that this morning I sent out the first teacher's message, and I consider that is the teacher's message of the week, of the first week. So it's a very important message because it is in this message that you're going to read the number of assignments you have, the number of quizzes you have, and also the scheduled day for the midterm exam. Now I use the blueprint of Professor C.M. Zhang. So basically, you will have how many assignments? Let's see. Starting from next Wednesday, you need to submit the first assignment, okay? And you all together should have 12 assignments, okay? So on specific sections of your textbook, not many. It's important that if you do calculus, and you must do some practice and solve some problems, do some thinking into it. Okay, so that is the schedule for your homework assignment. Now, the way you submit your assignment is you need to submit your assignment during the Wednesday tutorial. Okay, you must be there. But remember, before you submit the paper copy of the assignment, scan your copy into PDF document and submit your work on the same day through the submission link in the Moodle environment. I'm going to set up the submission link by the end of this week, so that you can see the submission links for individual assignments very soon. Okay? So, but remember, it is important that you submit a paper copy of your assignment to the TA, because through that you're going to receive a grade. Now, once you receive your assignment, the graded assignment with a grade there, you can scan it again and submit it to me through the system one more time. Okay, before the next assignment is submitted. Okay, so that is the procedure. So what I said here is very important. All those assignments are taken out from your textbook. This is the textbook, many of you are holding it already. And all the homework must be scanned first in the PDF document and submitted according to the following guidelines. The paper copy submitted to the TA during your Wednesday tutorial on a specific day scheduled there. And the PDF copy of your homework, which is not graded versions, must be submitted on the same day through the Moodle environment, okay? So you go to the library, you scan through it, and you send the scanned copy back to your email account at the Universal Accounts email, and then you can pick up your copy and you submit your copy to me, all right? So, and then, no late homework will be accepted because this is a rule, and the PDF copy of your graded homework will also have to be submitted after you've gotten it back from the TA, and the TA is going to give you the model answers of the graded assignment on the same week when you receive your graded homework, okay? So that is how the homework is being handled. Now through the homework, I guess you could get, I guess 15%? Or 10%, let's double check, it's about 10% of the semester work. And then you have the quizzes. You have 8 quizzes together in the semester, and all the quiz score will add up to 15%. So your first quiz is scheduled on January the 28th, okay? It's on Wednesday, tutorial sections, and each quiz is typically 30 minutes long. You will have to do 1 or at most 2 questions on the specific sections indicated here. You review the sections there, and then we're going to quiz you on the specific sections, all right? So it's basically, it's a give and take process. Now, then, for the quiz, all the quizzes are going to be done in the tutorial class, which is room 1021, if I remember correctly. And all the quizzes is going to be completed using A4 single line paper, okay? And when you write on this, write it concisely every other line so that we can see it very clearly. All the quizzes are supposed to be graded in 1 week, so 1 week after you take the quiz, on the next Wednesday, you're going to pick up the quiz paper with a grade, and model answers will be distributed. And then I'm going to ask you, once you receive the grade quiz, scan it through, produce the PDF document, and submit your PDF document through the Moodle environment so that I will have a record. So that is very important to do this minor step. And finally, the midterm exam is scheduled on March the 18th, Wednesday, tutorial class, which will last about 50 minutes. So it's on chapter 1, 2, and 3 from the textbook, all right? So it's basically, we set up the midterm, we set up the quizzes, we set up the homework, all right? So that is the very important teacher's message for this week. So you have something to do. Now, let me get back to the specific exercise that I invite you to do. Last Thursday. Now, I invite some of you, actually all of you, to do some review exercise on chapter 1, and I invite you to do some true or false on the specific sections of your interest. And basically, there are 4 sections, 1.1, 1.2, 1.3, and 1.4. Now, suppose you have already done those 2 or 4 sections. I have been asked, how are we going to submit those work? Well, it's very simple. So what you have to do is you come back here. If you want to keep it private yourself, just let me know. You go to week number 1, okay? And underneath week number 1, you have the hotline, Dr. Let's Q&A hotline, okay? So you can copy and paste the work here, because this is basically a forum. So when you come here, you create one discussion thread for one of those true and false exercises. They're all together, I guess, 4. So you may create one on 1.1, and you copy all the questions there, and you put your answer there, okay? Now I can take a look. And then I'm going to release the result or the answers on those possible questions by the end of this week. Now, another way for you to inform the whole class, if you don't mind, what you have done is you can copy some of this into the public online discussion forum. Now, if you do not want people to know all the answers of your questions, you may select some questions and post it here, and you want your classmate to discuss with you. If you select a true on a particular question, you want to see that it's everybody's idea, and you can invite discussions in. So all the work, you put it here, and selected work, you put it in the public online discussion, so that you can also see how your fellow students in this class look at the same question that you have been doing. And I tell you what, you can have a lot of inspirations from your fellow students' discussions. Sometimes the model answers may not work. Okay, the model answers may not work. I checked it already. Some of the model answers, I do not disagree. I do not agree, I better say, something like this. So I would prefer that we discuss together. But if you have done all this work, you want to ensure that your teacher, understand the work. Put it here, okay? Because when you put it here, only you and I can read it, okay? Not any other classmate in this class will read your hotline, except me. And then, if you have selected question you want to discuss with your fellow students, move it here and put your answers there and invite discussions. That is very interesting, okay? You can see that how people look at something. All right, I think I've already spent enough time here. Let's get back to the fundamentals of this week. Okay, now if you look at the textbook, sections 1.5 of the chapter 1, okay, we have something very important here going on, because the author spent some time here telling you what is calculus. Okay, let's try to see if I can focus a little. Focus. Yeah. All right. So in the context the author's idea, what he would like us to do is to think a little bit about the 2 fundamental problems in calculus. Okay. Yeah. I need to learn how to use that as a sensitive device. Okay, anyway, remember in the first class, last Monday, we tried to help you to understand what is meant by calculus, and in terms of that, we say the 2 branches of calculus, one is called the differential calculus, the other is called the integral calculus. And what is differential calculus going to do? And what is integral calculus going to do? Now, in the context of this textbook, sections 1.5, the author had given you very good answers, which is what I'm expecting. All right? So the two fundamentals of calculus is basically, one, it's the tangent problem. What is the tangent problem? Let's see, how can I manipulate this device in such a way that I could help you see that? Here we go. I want to stay there. Yeah. Can I do that? That's the user interface problem. Okay, I see. The light is on. Okay. You see, it's the resolution is okay. All right. So, what is the tangent problem? The tangent problem, basically, you read from your textbook. It's basically to be faced by what do we mean by the line tangent to any curve y is f of x at a given point. Okay? The tangent problem is basically faced as read page 45. The first fundamental problem is what do we mean by the line tangent to the curve y is equal to f of x at a given point. Okay? So tangent is a specific line touching on a particular curve. Okay? This is a very traditional concept. The second question, if you turn to page 47, okay, in the middle of page 47, is that the second fundamental problem of calculus is the problem of area. Okay? The first is the tangent problem. When we talk about the tangent problem, it's basically the slope. The slope. And the second problem on page 47 is the area problem. The area problem is basically given a curve which is y equal to f of x, what is the area between the curve and the x-axis over the interval, which is a closed interval, 2 point A and B. So differential calculus is basically concerned with the slope prediction problem. And the integral calculus is basically concerned with the area problem, which is to find the area under a particular curve between the curve and the x-axis. So now keep this in mind. We're going to start this week's calculus, and the topic for this week is basically, according to the syllabus, is limit and the concept of continuity. All right, keep that in mind. Let's go. Let's go back to the first week. Highlight the calculus. Let me introduce Professor Gilbert Strand from MIT. Okay, he's a very inspirational speaker, and he has been teaching calculus for many years. He would like to tell us something. Okay, and keep that in mind. You have 27 minutes with Professor Gilbert Strand. All right. Here we go. Read. Now, get ready your pens and piece of paper so you can put down some questions during the process of watching this lecture. Is Professor Gilbert Strand talking?
To be lost in the big calculus textbooks and the many problems and you're in the details, but do you see the big picture? Well, I hope this will help. For me, calculus is about the relation between two functions. And one example for those two functions, one good example, is function 1, the distance traveled, what you see on a trip meter in a car. And function 2, The one that goes with distance is speed. How quickly you're going, how fast you're traveling. So that's one pair of functions. Let me give another pair. I could give more and more, but I think if we get these two pairs, we can move forward. So in this second pair, height is function 1. How high you've climbed, if it's a graph, how far the graph goes above the axis. Up, in other words. So that's height, and then the other one tells you how fast you climb. The height tells how far you climbed. It could be a mountain. And then the slope tells you how quickly you're climbing. At each point, are you going nearly straight up, flat, possibly down? So distance and speed, height and slope will serve as good examples to start with. And let me give you some letters, some algebra letters that you might use. Distance, maybe I would call that F of t. So F for how far, or for function, and the idea is that t is the input. It's the time when you're asking for the distance. The output is the distance. Or in the case of height, maybe y of x would be the right one. X is how far you go across. That's the input. And at each x, you have an output y, how far up. So this is, F is telling you how far, y is telling you the height of a graph. That's function 1. Two examples of function 1. Now what about slope? Well, luckily speed and slope start with the same letter, so I'll often use S for the speed or the slope. For the second, you can stand for a second function. But let me tell you also the official letters that make the connection between function 2 and function 1. If my function is a function of time, the distance, how far I go, then the speed is, the right letters are D, F, D, T. Everybody uses those letters. So let me say again how to pronounce. D, F, D, T. And that Leibniz came up with that notation, and he just got it right. So, and what would this one be? Well, corresponding to this, looks the same. Or dy dx. Again, I'll just repeat how to say that. Dy dx. And that is the slope, and we have to understand what those symbols mean. Right now I'm just writing them down as symbols. May I begin with the most important and the simplest example of all? Let me take that case. So the key example here, the one to get completely straight, is the case of constant speed, constant slope. I'll just graph that. So here I'm going to graph. This is the, shall I make it the speed? Yeah, let's say speed. So time is going along that way, speed is up this way. And I'm going to say, in this first example, that the speed is the same. We're traveling at this constant speed of, let's say, 40. So it stays at the height of 40. I should add units, like miles per hour, or kilometers per hour, or meters per second, or whatever. For now, I'll just write 40. Okay, Now, if we're traveling at a speed of 40 miles per hour, what's the distance? Well, let me start with the trip meter at 0. So this is time, again, and now this is going to be the distance. After 1 hour, my distance is 40. So if I mark t equal to 1, I've reached 40. That's height 40. At t equal to 2, I've reached 80. At t equal to 1/2, half an hour, I've reached 20. Those points lie on a line. The graph of distance covered when you're just traveling at a steady rate, constant speed is just a straight line. And now I can make the connection. I've been speaking here about distance and speed. But now let me think of this as the height. 40 is that height, 80 is that height. And ask about slope. What is slope? So let's just remember, what's the connection here? What's the slope if that's the distance? If I look at my trip meter and I know I'm traveling along at that constant speed, how do I find that speed? Well, it's just slope. It's the distance up, which would be 40 after 1 hour, divided by the distance across, 40 over 1, or 80 over 2. Doesn't matter because we're traveling at constant speed, so the slope, which is up over across, is 40 over 1, 80 over 2, 20 over 1/2. But I'll put 80 over 2 as one example, 40. Oh, let me do it. That's arithmetic. Let me do it with algebra. We don't need calculus yet, by the way. Calculus is coming pretty quickly. This is the step we can take. Because the speed is constant, we can just divide the distance by the time to find, and this slope, let me write speed also, up over across, distance over time, F over T, that gives us S. This is S. Okay, what about calculus goes both ways? We can go both ways here. We already have practically. Here I went in the direction from 1 to 2. Now I want to go in the direction, suppose I know the speed, how do I recover the distance? If I know my speed is 40, and I know I started at 0, what's my distance? Distance, or height, either one. This is now, so these are like both. Now I'm just going the other way. Well, you see how. How do I find F? It's S times T, right? Your algebra automatically says, if you see a T there, you can put it there. So it's S times T, it's a straight line. S times T, S times X, Y equal SX. Let me put another, the same idea with my YX letters. It's that line. In other words, if that one is constant, this one is a straight line. Okay, straightforward, but very, very fundamental. In fact, can I call your attention to something a little more? Suppose I measured between time 2 and time 1. And I measure, so I'm looking between time 2 and time 1, and I look how far I went in that time. What I'm trying to, I'm going to put in another little symbol because it's going to be really worth knowing. It's really the change in F divided by the change in T. I use that letter delta to indicate a difference between, the difference between time 2 and time 1 was 1, and the difference between height 2 and height 1 was 40. You see, I'm looking at this little piece, and of course, the slope is still 40. It's still the slope of that line. Yeah, so that really, what I'm measuring in speed there, I don't always have to be starting at t equals 0. And I don't always have to be starting at f equals 0. Oh, let me draw that. Suppose I started at f equals 40, my trip meter happened to start at 40. After an hour, I'd be up to 80. After another hour, I'd be up to 120. You see that this starting the trip meter, who cares where the trip meter started? It's the change in the trip meter that tells how long the trip was. Clear? Okay. So that's that example. We come back to it because it's the basic one that where the speed is constant. And even if now I have to move to a changing speed, you have to let me bring calculus into these lectures. Okay, I'm going to draw another picture, and you tell me about let me draw function 1. Another example of function 1. So again, I have time, I have distance, I'm going to start at 0, but I'm not going to keep the speed constant. I'm going to start out at a good speed, but I'm going to slow down. Do you see me slowing down there? I don't mean slowing down with the chalk, I mean slowing down with slope. The slope started out steep and got, by that point, the slope was 0. What was the car doing here? The car is certainly moving forward because the distance is increasing. Here it's increasing faster. Here it's increasing barely. In other words, we're putting on the brakes. The car is slowing down. We're coming to a red light. And in fact, there's the red light right at that time. Now, just stay with it to think, what would the speed look like for this problem? If that's a picture of the function, just let's get some idea. I'm not going to have a formula yet. I'm not putting on all the details. Well, actually, I don't plan to put in all the details of calculus, or every possible step we might take. It's the important ones I'm hoping to show you, and I'm hoping for you to see that they are important. Okay, what is important here is, roughly, what does the graph look like? Well, it started out, the speed, the slope, started out somewhere up there. Started out at a good speed and slowed down. And by this point, let's mark that time here on that graph. Do you see what is the speed at that moment?
0.
The speed at that moment is 0. The car has stopped. The speed is decreasing. Let me make it decrease, 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 decrease. And at that moment, the speed is 0 right there. That's that point. See, two different pictures, two different functions, but same information. So calculus has the job of, given one of those functions, find the other one. Given this function, find that one. This way is called, from function 1 to function 2, that's called differential calculus. Big, impressive word, isn't it? That's function 1 to 2. Finding the speed. Going the other direction is called integral calculus. The step is called integration. When you take the speed over that period of time and you recover the distance. So it's differential calculus in one direction, integral calculus in the other. Now, here's a question. Let me continue that curve a little longer. I got it to the red light. Now imagine that the distance starts going down from that point. What's happening? The distance is decreasing. The car is going backwards. It's going in reverse. The speed, what's the speed? Negative. The speed, because distance is going from higher to lower, that counts for negative speed. The speed curve would be going down here. You see that that's a not brilliantly drawn picture, but you're seeing that that's the farthest it went. Then the car started backwards, and the speed curve reflected that by going below zero. You see the two different curves, but same information. I'm remembering an old movie, I don't know if you saw it, an old B movie called Ferris Bueller's Day Off. Did you see that? So the kid had borrowed his father's, not borrowed, but lifted his father's good car and drove it a lot, like so, and put on a lot of mileage. The trip meter was way up, and he knew his father was going to notice this. So he had the idea, put the car up on a lift, put it in reverse, and go for a while, and the trip meter would go backwards. I don't know if trip meters do go backwards. It's kind of tough to watch them while going in reverse. But if whoever made the car understood calculus as you do, the speedometer, maybe, now that I think of it, speedometers don't have them below zero. They should have. And trip meters should go backwards. I mean, a calculus, that movie was just like made for a calculus person. Maybe I'm remembering more. I think it didn't work or something. And the kid got mad and kicked the car, and it fell off the lift, went through the glass window. It was, anyway, calculus would have saved him if only the car had been, or the meters in the car had been made correctly. All right, that's one pair. That's our first real pair in which the speed changes. Okay. I thought in this first video, if you, later, even today, I'll get to a case where we have formulas. That's what calculus moves into. When f of t is given by some formula. Well, here it's given by a formula, s times t. A simple formula. And then, knowing that, we know the speed is s. Later, we got more functions. But let me take an example, just because these pairs of functions are everywhere. What could I take? Maybe height of a person. Height of a person. Okay, so this is now another example, just to get practice in the relation between the height of a person and the rate of change of the height. So this is the height. Maybe I'll call it y, but let me write height of a person. And what is this going to be? What is function 2? Well, slope doesn't seem quite right. The point about function 2 is it tells how fast function 1 changes. It's the rate of change of the height. It's the rate of change. So let me call it S, and it'll be the rate of change. Good if I use those words. Yeah, so I want to think about how we grow, typical person growing. In fact, as I wrote this on the board, I thought of another pair. Can I just say it in words, this other pair, and then I'll come back to this one?
Sure.
Here's another pair. This could be money in a bank. Wealth sounds better. Let's call it wealth. That's zippier. And then what is this one? If this is your wealth, your total assets, what's your worth? This would be the rate of change. How quickly you're saving. S could be for saving. Or, if you're down here, S is for spending. Right? If S is positive, that means your wealth is increasing, you're saving. Negative S means you're spending, and your wealth goes whatever. Maybe, I hope, up. Height is mostly up, right? So let me come back to height of a person. Now, and this is time in years. This is T in years. And this too, of course. Actually, I realize you start at T equals 0, birth. You do start at a certain, actually, what do I know? You don't say tall, you say long, but then as soon as you can stand up, it's tall. So let's say tall. So guess 20 inches. If that's way off, I apologize to everybody. Let me just say 20. 20 inches. Okay, at year 0. Okay, and then presumably you grow. Okay, so you grow a little. What are we headed for? About 60, 70 inches or something. Anyway, you grow. Let me put in some, let's say that's 10 years old and here's 20 years old. Okay. So you grow. Maybe you grow faster than that. Let's say you're a healthy person. Okay, up you grow. Okay. And then, at about maybe age 12 or 13, there's a growth spurt. And maybe the point is, how do we see that growth spurt on the two graphs? Differently, but it's the same growth spurt. Okay, so here your height suddenly jumps up. Boy, you catch up with everybody. And then, at about 12 or 13, well then unfortunately it doesn't do that much forever. And it kind of levels off here. levels off, and actually you don't grow a whole lot more. In fact, I think when you get to about, well, I don't know, whatever, we won't discuss this point. I think if you get too old, you probably lose some. Let's not emphasize that. Okay, so here's the, now what's happening over here? Well, it's the slope of that graph. So the slope might be, this is time 0, but you're growing right away. You don't, the S graph, the rate of growth graph, doesn't start at 0. It starts how fast you're growing, whatever you're growing, whatever that slope is. It's fantastic that when we draw graphs of things, the word slope is suddenly the right word. Okay, so you're growing, maybe at a pretty good rate here. And let me mark out 10 and 20 years. And okay, you're doing well. Coming along here. And then the growth spurt. Okay, so then suddenly your rate of growth takes off. But it doesn't stay that way, right? Your rate of growth levels off. In fact, levels way off. Levels, you come down here and then you probably don't grow a lot. You see the two? This was the growth curve. This was the fast growth. But then it stopped. Up here it slowed down. Here it dropped. And, if we allow for this person who lived too long, height actually drops. Okay. There's an example in which I don't, also I'm sure people have devised approximate formulas for average growth rates, but you see it's the idea of the relation between function 1 and function 2 that I'm emphasizing. Now, my last example. Let me take one more example. One more example for this first lecture. So let me take a case in which the speed is. So here will be my two. So let's use speed. Let's use this is distance. This is distance again. And graph 2, as always, will be speed. And I'm going to take a case in which it's given by a formula. I'm going to let the speed be increasing steadily. Okay, so my speed graph this time is going to go up at a constant rate. So this is the speed S. This is the time t. So this would be S equals, S is proportional to t. That's where you get a straight line. S is, let's say, A times t. That A, the physicist, if we were physicists, would say acceleration. You're accelerating. You're keeping your foot on the gas, steadily speeding up, and so then S is proportional to t. Now, think about the distance. What's happening with distance? If this is accelerating, you're going faster and faster, you're covering more and more speed, more and more distance, more and more quickly. If this is slope, the slope is increasing. Look, the graph, let's start the trip meter at 0. So you started with a speed of 0. You were not really increasing distance until you got slightly beyond 0, and then it slightly started to increase. But then it increases faster and faster. Right? Never gets infinitely fast. But it keeps going upwards. And the calculus question would be, can we give a formula, an equation for the distance? Because in this case, I guess I started with function 2, and therefore it's function 1 that I want to look at. It's always pairs of functions. Okay. Now, so this actually, let's think where this would actually happen. If we were leaning over the Tower of Pisa or whatever, like Galileo, and dropped something, or even just dropped something anywhere, that would be, we drop it at the beginning, it has no speed, but of course instantly picks up speed. The A would have something to do with a gravitational constant for the Earth, whatever, and then maybe, yeah. And what would be the distance? Okay, now can I just mention a small miracle of calculus? A small miracle. I'm going this direction now from speed to distance, so I'm doing integral calculus. And we'll get to that later. In the first lectures, we're almost always going from 1 to 2. But here's a neat fact about going from 2 to 1. That if this is the time t, then of course this height here will be 8, that'll be a times t. And the amazing fact is that this graph tells you the area under this one. Graph 1, function 1, tells you the area under the graph 2. And in this example, with a nice constant acceleration, steady increase in speed, we know this. This is a triangle. It has a base of t, it has a height of at, and the area of a triangle, of course. The area, and my point is that the area is function 1, amazing. That's just terrific. Will be the area of this triangle here is 1/2 of the base times the height. That's the area, and calculus will tell us that's function 1. So this function is, this is 1/2 of a times t squared. So there is a function 1, and here is df dt. If I go back to the first letters that I mentioned, if this is my function f, then this is my function, and notice what kind of a curve that is. Do you recognize that with a square? That tells me it's a parabola. A famous and important curve, and of course it's important because it has such a neat formula. Okay, so we have found the function 1. We've recovered the information in that lost black box, the distance box, the trip meter, from what we did find in black box 2, the speed, the record of speed. And notice I'm using the speed all the way from here to here. The speed kind of tells me how the distance is piled up. The distance is kind of a running total, where the speed at that moment is an instant thing. Oh, we have to do that in future lectures. The difference between a running total of total distance covered, and a speed that's telling me at a moment, at an instant, how distance is changing. The slope at this very point T, that slope is this height, is AT. Okay, so there you have the first, well, I'll say the second. The first pair of calculus was this one, F equal ST, and its derivative was S. Our second pair is F is this, and will you allow me to write dF dt? If F is 1/2 of AT squared, then dF dt is AT.
Wow.
You'll see this rule again. The power 2 dropped to a power 1, but the 2 multiplied the thing, so it canceled the half and just left the end. Okay, that's a start on the highlights of calculus. Thanks.
This has been a production of MIT OpenCourseWare and Gilbert Strang. Funding for this video was provided by the Lloyd Foundation. To help OCW continue to provide free and open access to MIT courses, please make a donation.
Here we go. I've given you a preview into what you're supposed to learn in calculus by studying from sections 1.5 of your textbook, chapter 1, where the author has given 2 fundamental problems that we are going to study in the context of calculus. In the post-section of calculus 1, we are going to finish the first problem and touch a little bit on the second problem. And the first problem belongs to the differential calculus. It had something to do with understanding the tangent to a specific curve. And the second problem, it's about the area between a specific curve and the x-axis. Now, in the context of Professor Gilbert Starn's introductions, he has used a lot of very simple, intuitive examples to guide you through the thinking process. And what I would like you to do when you go home, before you come back to our second class on Thursday, is you go home and watch this video, just 37 minutes and 46 seconds, as many times as you want, okay? Pick up something which you believe, oh, I can definitely accept this argument, but pinpoint on those examples an idea that Professor Starn had used that makes you feel a little bit confused, okay? And then make the best use of our discussion forum for this week and try to pose your questions here, okay? This is week number 2. We have a public online discussion forum here, all right? So you can actually copy and paste some of the work, all right? And then ask questions. Now remember, here is the MIT's course on big picture calculus. Here is called a highlighted calculus produced by Professor Gilbert Strang. There are 5 videos here. This is the first video, all right? If you're interested, definitely go through the other videos, just a couple of minutes. And get your head start on that. In the meantime, ask yourself this question. Make sure you finish reading that. From page 45 to page 48, okay, of your chapter 1, before you come back on Thursday, read these several pages, including the examples provided by the author of the textbook, all right? And then match out with the examples that you saw in this video. And this is very important. It's a very simple homework exercise before you come back to class. In the meantime, let me remind you, now I will start putting things in order. This is week number 2. Normally, what I invite you to do before class, I'm going to tell you through this link, okay? What we are going to do during class, if you click here, you will know something about this. What I'm supposed to invite you to do after class, click this link and end the week, okay? So I will try to put this in order during this week. In the first week, I did not put them in order. All right, so if you happen to forget what I said just now, come back to click on this link to read what you're supposed to do before you come to class on first day. Okay? So I'm going to set it up basically tonight. Alright? So you understand the setup of the system. And then, now let me tell you a little bit more about this. Last week, I have already installed the first week class questionnaire here. And many of you have already done this, but there are 34 students in this class. And so far, how many of you have already done this? Only 16. Now you know how to do calculations. 34 minus 16 equal to what? 34 minus 16 equal to what? 20 something? Or 15 something? Okay, that you know, if you happen to be the person who have not done this questionnaire, make sure you finish doing it before 11:55 tonight. Okay, 11:55 tonight is the deadline to close this questionnaire. Alright? So make sure you come to finish the questionnaire. It's very important you let me know something. Alright, so the questionnaire is right here. It's going to end tonight at 11:55 p.m. So if you have not done this questionnaire, make sure you finish it, okay, before 11:55 tonight. Okay. Starting from this week, besides inviting you to get yourself ready before class, besides telling you what we're going to do during class, I'm going to introduce also a thinking exercise to you in each of the class, just like what I did. I invite you to study a little bit about the book. The book often gives you some basic hints on what you're going to study. And I've given you some video to stimulate on you. And then it's time for you to put into informations, the topics, some of your thinking. And then so on first day, when I invite you to do something in class, you will be ready, all right? So remember, this week, the topic is limits and the concept of continuity. Do you remember? If you want to know something more about this, go to the reading of this week, okay? At the end of the week, you're supposed to finish reading the second chapter, just like the first chapter. I've already put down some main points here. Not all of these will be equally important, but you have to go through them. So this week, according to chapter 2 of the textbook, the first section is tangent lines and slope predictor, which comes directly in connections with parts in the first chapter on the different type of functions. And then on section 2 is the limit concept, and it's study of the limit concept, the idea of a limit, and then some kind of laws, and more about the limits, okay? Now, you are not here to memorize all of these, no. And then we come to the concept of continuity. Again, I've given you some link through the intellect where you can get some quick refresh on ideas on limits and continuity. Okay? So all of these are more than enough resources for you to have a basic understanding or advanced understanding or master of the concepts. So, are you ready for the next class? What are we supposed to do now? Take attendance. Here we go. Dear, are you here? Sun Zhuang Gun. Sun Zhuang Gun. My graduates, not good. Cornell. Cornell, not here. Licky. Not here. Licky. Okay. All right. So, Terry. Thank you. Eden, thank you. Jason, not here today, okay. Oh, he's sleeping. Okay. Yeah, he's thinking. No, he's thinking. He's not sleeping. Kerwin.
Yeah.
Thank you. Joy. Thank you. Amy. Thank you. Susie. Thank you. Joelle. Thank you. Bob. Thank you. Sean. Thank you. All right. Nietzsche. Thank you. Nuana. Thank you. Niu Hongyuan. Thank you. Can't bear with me. Okay. Sue, thank you. All right. Pete. Thank you. Elaine, thank you. Kent, thank you. Anson, thank you. Wong Xin-Han, are you here? Not here, okay. Kim, thank you. Simon, are you here? Simon is not here, okay. All right, so Angela, thank you. Sting, thank you. Susan, thank you. And then there's Ming, thank you. Aura, thank you. Logo, thank you. Jackie, thank you. Amber, thank you. Yan, not here. Okay, thank you. Or any person whose name has not been called. Okay. Now remember, I'm going to tell you a little bit more about note-taking because I've already got questions for reading the first bit of the week questionnaire. How are we going to take notes? Now basically the notes could be taken directly from the textbook where you put down some important points, mark down some equations. Notes could be taken from the video, from the extra resources given. But when you take note, make sure you cite the source, okay? And the notes could be taken on a small piece of paper, or the best one is to take it in a notebook, and then you reorganize them and type it in using Moodle environment. Oh, how are we going to type equations in the Moodle environment? I'm going to get you some tutorial probably next week. There are some tools in the Moodle environment to type very sophisticated equations, okay? So, and then I'm going to tell you a little bit more about note-taking, all right? Okay, now I have 5 more minutes to put into perspective some of the context of today. When you look at the videos produced by Professor Gilbert Swan from the MIT, so what do you discover from watching this video that makes you impressed? What is it in the video that makes you so impressed? Did he do a good job in helping you to understand the basic concept? The graph represents what? It's a real-life example of something, okay? He's trying to think of something simple, something practical enough for you to understand something complex. Now, he's always trying not to give you a lot of the idea first. He's often using something very simple. Let's not talk about calculus, let's talk about algebra by fixing something. And then he said, okay, now let's bring in calculus. And when he said, let's bring in calculus, what is he talking about? Okay, before you walk out of the classroom today, remember, one graph is a very simple graph. It's talked about at a certain point in time, you can read a specific number which represents a specific entity, like the distance traveled, the height of a person, or the weight of a person. Okay, this is very simple first graph. What is the other graph? He's trying to help you to understand calculus. And he talks about this, the other graph as what? Remember in first class last Monday, when we tried to look up the meaning of calculus using Wikipedia, what is the key word that we use to describe calculus? Change. So in the second graph, what did he use to represent the second graph? Rate of change. That means how fast this change is going to happen, or how slowly this change is going to happen. Okay, the rate of change. So calculus is about the rate of change of something, and it's about given a particular functions or given one piece of information, you're going to look up another piece of information, and in the context of his lecture, he's always telling you calculus is about the relationship between two functions. Given one, you use the information given one to find the other, or you were given the information to the other, you find the other. So in one direction it's called differential calculus, in the other direction it's called integral calculus. Now in the context of calculus 1, we're more interested in the rate of change of something. And if you look at the examples given in your first chapter, you can see that there are a lot of functions of different characteristics which you can use to help in our problem solving. Okay? So let's return to this class on Thursday to start looking at something much more interesting. And in the meantime, feel free to put forward your questions through your public online discussion forum here, or even through documents given online. Okay? Thank you very much. That's it for today. It's time to go. All right? So that's it for today's MATB 110, Section 1, Calculus 1 on January 12, 2015. Until this Thursday, stay tuned.